Hello and welcome to our presentation on provisioning infrastructure as code using GitLab and Terraform. I'm Julian Vandenberg, and with me today is Brian Hill. We are software developers working on applications for the Office of the Registrar, and today we are going to talk to you about how we used Terraform and GitLab together in our residency application, as well as some lessons we learned along the way. First up, we'll give a brief overview of the Residency App. We'll move through some Terraform basics as well as how to get set up with Terraform. We'll then move on to a few technical specifics of how we integrated Terraform into our development workflow. Finally, we'll finish off with a segment on how to handle service account credentials and how to integrate Terraform into your existing application. The residency application is used by prospective students to automatically determine whether they qualify as Wisconsin residents for tuition purposes. A major user experience feature is the ability to save in-progress applications and return later without having to re-enter any fields. Older versions of this application required the entire application to be completed at once, which could be a challenge given the application's length and detail. The Residency app is separated into a front-end and back-end project. The whole thing was deployed using a serverless architecture and doesn't require Apache or Shibboleth for authentication. The front end is written using Angular, and the back end is written in Go. A number of AWS services are used, including DynamoDB, SQS, SNS, Amplify, Lambda, and a handful of others. Now that we've gone over the different components of our residency application architecture, we can talk about how we use infrastructure as code to manage and provision some of these components within AWS. Infrastructure as code is the managing and provisioning of infrastructure with code and configuration files instead of through manual processes. It allows you to build, change, and manage your infrastructure by defining resource configurations that you can version, reuse, and share. Terraform is the infrastructure as code tool that we use to define resources and infrastructure in human readable declarative configuration files, which helps us manage our infrastructure lifecycle. The Terraform components that we need to know about are Terraform files and state files. The Terraform files are the set of configuration files used to describe infrastructure that is created by the developers and the development team. When you apply your configuration, Terraform writes data into a state file, which reflects the current state of infrastructure managed by the plan. Terraform stores the IDs and properties of the resources it manages in this file so that it can update or destroy those resources going forward. The state file often contains sensitive information, so it must be stored securely and have restricted access. We'll go over how we store the state files for our application in a later slide. The Terraform workflow generally follows a three-step process. First off, Terraform examines the infrastructure referred to by the plan. If the resource doesn't exist, it will be created. If it exists and matches, no changes will be made. If it detects differences, Terraform will do its best to modify the resource in place. If that's not possible, it will destroy and recreate the resource. Next, the developer views the changes that Terraform intends to make with the Terraform plan command. If the contents of the plan command look good, the developer uses the Terraform apply command to create, update, or delete the resources in the Terraform files. Now that you know a bit about how Terraform works at a high level, let's take a look at how you would begin to set up Terraform for an application. The provider block configures the account associated with the application and determines the type of infrastructure being defined. This is where you'll tell Terraform which plugins or providers you'll be using, as multiple providers like AWS, Google Cloud Platform, and Azure are supported. Within the provider block, you can specify settings such as which account IDs the configuration can allow in order to make sure you don't apply a configuration to the wrong account, which region the configuration will deploy to, and you can add some tags for analytics. The backend block defines where the Terraform state file will live. In the example on the screen on the right side, we are indicating that the state file will be stored in an AWS S3 bucket called a residency-app-tf state. Storing state files in S3 buckets is considered a good practice for reasons we'll get into later, but it's considered a good practice this might raise a question for you. How are we supposed to use an AWS resource for our state file if we don't have the state file yet to create the S3 bucket? This is an example of a chicken and egg scenario, or more formally, a circular dependency. The solution to this circular dependency problem is to manually create the S3 bucket ahead of time, whether that is with the AWS CLI or in the AWS console. Since we only anticipate on creating the S3 bucket once, it's probably sufficient to just create it and be done with it. However, you may also want to create a shell script to save the commands for disaster recovery purposes. Above is an example from our repository showing the two AWS S3 API commands we use to set up our S3 buckets. We've been talking about storing the state file in an S3 bucket, and while we have other options for this, such as versioning the file alongside the application files, the S3 method is the recommended approach for a few reasons. Those of you familiar with version control systems know the challenges that come about when multiple contributors try to make changes to the same file. By keeping the state file out of a version control system, you minimize the chances of unintended changes or side effects reaching your state file and affecting your infrastructure. An added benefit is that S3 allows you to maintain a complete version history of the state file, as well as take advantage of encryption at rest. Encrypting the state file is important for reasons we'll touch on later. Next, we'll go over integrating Terraform with the Gitlab CI/CD tool. Gitlab CI/CD is the part of Gitlab that you can use to automatically test, build, and publish your code. We use the Gitlab CI/CD tool to run the Terraform commands necessary to validate our Terraform configuration files and apply them to provision our infrastructure and update the state file. The Terraform commands used in the standard workflow are organized in the CI/CD tool in GitLab. Artifacts containing details about the actions of the pipeline can be generated to deliver developer-facing reports. And CI/CD variables are available for use in Terraform commands, fully integrating data from the deployment process into your Terraform files. New features exist, but for the most part, we haven't tried them yet. Most of the points in this section can be used in any version control system and aren't specific just to GitLab. These are the Terraform commands that we use in our GitLab CI/CD pipeline to automatically create the Terraform resources. In order to do this, these commands are included in the project's GitLab CI file. I won't read out the commands in detail here, but these are the commands you'll find yourself using most often when designing your own pipeline. Here's a snippet from the GitLab CI file that initializes, formats, and validates the Terraform configuration files before applying the changes. In this step, we will be able to see the actions that will result from the Terraform plan without actually committing to those actions. Once the validate step is completed, we can move on to creating our infrastructure in a deploy step that looks like the one pictured here. The key is the Terraform apply command about 2/3 of the way down in the screenshot, which applies the changes proposed in the plan. Here is an example of how you can integrate the data from the Terraform plan into your code review process to quickly review the changes that Terraform will make. The screenshot on the top is a small report showing the number of changes Terraform plans to make, and the screenshot below is the code in the GitLab CI file responsible for generating the report. If you wish to create this feature in your own application, there's a link at the end of the slide deck that you can use as a reference. We're going to switch over to Brian now, who will start off by discussing how to implement multiple application environments in this process.
Let's look at ways to handle differences between your environments, such as development, QA, and production when provisioning them with Terraform. For the residency application, we primarily did local application development and then deployed to test and production tiers in AWS. Let's see how we configured this in Terraform. As a best practice, we like having our tiers in separate AWS regions. By convention, we use US East 2 for production and US East 1 for our test and development. Our goal is to have one Terraform configuration for all of these AWS environments. In other words, we want Terraform to create the exact same objects in test and production so that we can have a reasonable expectation that production will perform the same as the test environment. To achieve this, we can configure Terraform to use separate state files for test and production. We can also use GitLab CI/CD files use GitLab CI/CD variables rather to pass environment-specific values to Terraform. For example, we can specify the AWS region for each environment to be provisioned in. So how do you manage the different configurations between your environments if the Terraform code is the same between your test and production plans? One way is to use Terraform variables. For the residency application, we use an environment variable to pass in the application version so that the Terraform will know which version of our code to deploy to each environment when deployed from the GitLab CI/CD pipeline. We like having a dedicated Terraform variables file that holds all of our customizable variable keys so that we have one place to find them instead of looking through the other files that hold the object definitions. Values can be passed to Terraform explicitly on the command line using the -var option or by setting the tf_var environment variables. These values might simply be the name of the prefix to use for the tiers, such as test or prod, or they may be the full resource identifiers or names if there is no other way to specify a given resource, such as an existing VPC. One of our lessons learned is that it's important to think about naming conventions. But in the AWS console, it can be very confusing as to which environment you're working in because region is a simple dropdown in the upper right-hand corner. Using the environment or tier name and the object name can help avoid confusion. Another consideration is dealing with existing infrastructure that may have inconsistent names. In these instances, you can use conditional operators to account for the differences, but we've tried to minimize this as much as possible because it can make the code longer and more difficult to understand, as seen in the second code example at the bottom. Most applications are going to need to talk to other applications at some point, whether it's a database or an external service, and it will probably need some sort of credential to access it, like a username password pair or an API key. There are a lot of different ways to manage credentials in the cloud, and a lot of them might be bad ideas. Let's look at the ways you might provide an application with credentials it can use for a database connection. You could include it in a file on the disk. You could include it in a deployed artifact like a WAR file or a zip file. You could inject it into the application's environment as an environment variable. And you can also have the application fetch it using an API from somewhere secured. The first option, putting it in a file on the disk the application runs on, is a venerable strategy, but it doesn't work very well in the cloud. Since clustered VMs are auto-provisioned and might go away at any time and get replaced, you would have to include setting up the credential file on the VM as part of the provisioning script. In a serverless context, you might not have a local disk to put the credentials on, and it's not likely to persist if you do. The second option, including it in the deployed artifact as a property file or in some other way, isn't a great idea for several reasons. It's not necessarily secure enough, and you would need to provide extra do-it-yourself security layers like encryption throughout the build and deployment workflow. It also means you probably need to redeploy the application artifact to change the embedded credentials. The harder it is for you to rotate credentials, the less frequently you are likely to want to do so. Having the application read the credentials from environment variables is a solid choice, but how do the credentials get into the Terraform? How do the credentials get into the environment, rather? You can put them right into the Terraform plan to populate the application's environment with them, but that's not much different than hard coding them into the application. And they're likely to end up in Git that way, which is generally bad. The third option is probably the most secure and modern, but requires code changes for each application and each platform you'd like to deploy the application on. At AWS, this service is called the Param Store and provides a full API to read and write keys in a secure and values like credentials and service URLs in a highly secure manner. We can combine the latter two strategies by using a capability of the Param Store service to inject a value into the execution environment directly from the Param Store. Since you can use the cloud platform's IAM system to restrict access and use of the Param Store service, this allows you to safely store credentials in the Param Store and securely access them through environment variables in the application. Terraform can configure an application deployment to populate certain environment variables like credentials directly from the Param Store by referencing their Param Store keys. The best practice is to name the param store keys as virtual paths, since there are API operations that act upon key prefixes, so you can easily create a virtual hierarchy of parameters by using path expressions. So how do the credentials get into the parameter store? You could certainly hand enter the credentials right into the parameter store pages in the AWS console. Once it gets in there, it's as secure as if you entered it any other way. But there are good reasons to be able to replicate and automate setting up the parameter store with all the parameters that your application needs, most important of which is that your application needs them to operate. So we should make sure to find a way to ensure their existence. There's a full feature set of Terraform definitions for working with the AWS param store, so it's easy to create the param store variables and application needs in the same Terraform plan as the application infrastructure. You can configure a variable in a Terraform plan to ask for the value that should be used when it's getting applied to the infrastructure, so you don't need to include it in the source code of the plan. However, you might not want to have to enter all of the database and other credentials every time you update your application. For one thing, you don't need to, since the credentials haven't changed. You also need to have the credentials available when you redeploy the application, which adds another constraint that nobody should want or need. One principle that's useful to apply when designing Terraform plans is to consider the expected frequency that you will need to change the infrastructure in the plan, and split out pieces that change frequently from those that rarely change into separate plans that would be applied separately. For example, you could create one Terraform plan that creates the param store parameters for the application and is expected to run in an environment where the credentials can be hand entered or securely passed on the command line, and then create another Terraform plan that deploys the application itself that references these param store entries. You only need to apply the param store plan when you change the application service credentials, and you can run the application deployment plan anytime you need to update and redeploy the application without needing access to the secured credentials. Next, please. Since Terraform needs to know when things are changed in order to track their state, it records all aspects of the infrastructure in the Terraform plan in its Terraform state file. This can often include credentials and other sensitive information. If you provision your param store entries with a Terraform plan, the state file will contain credentials in it. Even if you don't end up with credentials in your Terraform state files, such as if you hand entered the actual credentials via the AWS console, the state file contains a detailed and actionable map of your entire provision infrastructure. To a malicious hacker, this information would be incredibly valuable, since it would help them target vulnerabilities with great accuracy without the risk of discovery. So even without credentials, you wouldn't want to make it publicly accessible. If you follow best practices and keep the S3 bucket or other storage location for the Terraform plan state files secured using the platform's access control system, that should be sufficient, but don't keep it in a location with broader access than is strictly needed. It only needs to be accessible to the locations and roles associated with whatever or whoever is applying the Terraform plans, such as a CI/CD system or a developer's login. A lot of what we discussed so far has been oriented towards either creating new resources in your application or starting with a new application altogether. However, you can also integrate a Terraform configuration into an existing application to get the benefits of infrastructure as code from something you've already built. There are a couple of ways to utilize existing elements of your application, and the first one we'll discuss is the import statement. Terraform only modifies resources that it is responsible for. So how do we tell Terraform to be responsible for something that already exists? For that, we use an import command. In the example above, we're using the Terraform import command to import an existing Lambda function named Residency App and associating it with a Lambda function resource in our plan, also named Residency App. This will put Terraform in charge of managing the Lambda function resource in AWS. Once you run the import command, you can alternate running the Terraform plan command that tells you the changes that will be made, and modifying the definition of the Lambda function in your Terraform plan until Terraform reports that no changes are needed. This means that the description of the imported infrastructure component in your plan exactly matches what currently exists in the cloud. If you skip this step, you may end up with unintended changes to your application, since Terraform will modify the infrastructure that it manages to match the specification in the plan when you apply the plan. The other way to reference existing infrastructure in a Terraform plan is through data statements. A data statement performs a query against the provisioned cloud platform, and since it knows what type of resource it is looking for, it provides data about the resource you can use in the rest of your Terraform files. The example at bottom is a data statement that exposes data related to an IAM role resource and allows you to use it elsewhere in your plan, such as if you wanted to grant that existing resource to an AWS component you are provisioning in your plan. Since Terraform isn't responsible for the resources and data statements, or it may not be, you can delete a data statement without having any effect on the existing resource it refers to. When integrating Terraform with an existing application, while it's certainly useful, there are some associated risks. It is important to add the definition of a resource to your Terraform plan after importing it. If you don't do that, Terraform will think you no longer want that resource since it isn't reflected in the Terraform plan and will assume that the resource should be deleted. The definition in the Terraform must also match the current state of the provisioned resource, or Terraform might delete and replace or modify the resource to match the definition in the plan. In addition to this, it can be a good practice to split out different parts of your application into different Terraform plans based on the scope of the components you're working with. For example, the VPC and subnets of an application could be separated out into a base infrastructure plan, while the other components live in one or more feature-specific plans that refer to the infrastructure in the base plan using data statements. This generally minimizes the possibility of something going wrong in one plan affecting a resource in the other. This is often referred to as minimizing the blast radius of a Terraform plan. The Residency App project and this presentation were collaborative efforts from the entire road team. Below are some links you may find useful if you wish to put the material in this presentation to work in your own applications. Thank you.